Hi, welcome to Common Core Algebra II. Today's lesson is 4.13, Compound Interest. In the world of investment and debt, interest is added onto a principal in what is known as compound interest. The percent rate is typically given on a yearly basis, but could be applied more than once a year. This is known as compounding frequently. Let's take a look at the typical problem to understand how the compounding frequently changes how interest is applied. So exercise 1, just going to slide this up a little bit. A person invests $500 in an account that earns nominal yearly interest rates of 4%. So nominal yearly interest rate of 4%. How much would this investment be worth in 10 years if the compounding frequently was once per year? And show the calculation you used. So simple, what we talked about before would be our initial times 1 plus our rate, which of course is 1.04 raised to the 10th power, is equal to 740 point something something something, but we round it to the nearest cent. So we're talking about $740. B says, if on the other hand, the interest was applied 4 times per year, known as quarterly compounding, why would it not make sense to multiply by 1.04 each quarter? Well, because then instead of only doing it 10 times, so if you think about what we just did, we did 500 times 1.04 raised to the 10th power. So here we'd have to raise it to the 40th power, right? Because it would compound 4 times a year. And obviously that's going to give us an awful lot more money than $740. So basically there you're just going to write, because it's going to give you more than just compounding 4% per year. All right, so we can't do that. C, if you were told that an investment earned 4% per year, how much would you assume it earned per quarter and why? Well, per quarter, if we talked about it, would be, if you're talking about 4% per year, per quarter would be 4% divided by 4, which means that it earns 1% per quarter. I think that makes sense, right? And then using your answer from part C, calculate how much the investment would be worth after 10 years. Now remember, our original investment was $500. So we had $500 times, if we're still increasing, so it's going to be 1 plus. Now we could put 0.01. This could represent 0.01. So you could put 0.01 here, but you could also put that 4% that we had divided by 4, because it's 4 times per year. Now, how many times are we going to be doing this? For 10 years, we're going to do it for 10 years, but 4 times per year. So basically, you could have put 500 times 1.01 to the 40th power, which turns out to be $744.43, which makes sense. All right, so write down what you need to, and let's go on to exercise 2. So the pattern is fairly straightforward. For a shorter compounding period, we get to apply the interest more often, but at a lower rate. So exercise 2 says, how much would $1,000 invested at a nominal 2% yearly rate compounded monthly? So 2% yearly rate compounded monthly be worth in 20 years. Show the calculations that lead to your answer. All right, so if we consider our $1,000, and we're going to multiply that by 1 plus, now I'm going to remind you, we deal in decimals, 0.02. So 0.02, but how many times are we going to be calculating that? Monthly, 12 times for the next, we talked about 20 years. So that's going to be 20, but we're doing it 12 times. So it's going to be 20 times 12. All right, so you put this whole thing into your calculator and you get 1491.328. And this is a multiple choice question, so very easily we can see that number 2 is our correct answer. All right, so rewind that if you need to go through it one more time. All right, and remember we talked about, let me see if I can just quickly just go back here. And look and see that here it's our rate, but it's divided by 12 because we're talking about doing it 12 times a year. And then make sure that when you are raising it to your power, you're raising it to your 20 years times how many times you are calculating that per year. All right, so let's move back and go over to exercise 3. So this pattern is formalized in a classic formula from economics that we will look at in the next exercise. So exercise 3. Whoops, way to go. Here it is. Oh, that's 4. So for an investment with the following parameters, write a formula for the amount the investment is worth A after T years. So A of T is equal to our principal, all right, or our initial amount, P, times, remember we talked about it, 1. In this case, we're talking about interest, so it's always going to be 1 plus. And if N is the number of compounds per year, and R is the nominal yearly rate, we know this is going to be R divided by N, and then raised to the number of compounds per year times the time. So N T. Remember, we talked about after T years right here. So there is our formula, and that's the formula we're going to continue to use. The rate in exercise number 1 was referred to as nominal in name only. It's known as this because you effectively earn more than this rate if the compounding period is more than once per year. Because of this, bankers refer to the effective rate, or the rate you would receive if compounded just once per year. Well, let's investigate this in exercise 4. So an investment with a nominal rate of 5% is compounded at different frequencies. Give the effective yearly rate accurate to 2 decimal places for each of the following compounding frequencies. Show your calculations. The key in each of these cases is to determine how much we would have multiplied by after 1 year. Then we can use this to determine the effective yearly rate. So if we consider quarterly, quarterly is going to be 1 plus, remember it's 0.05, I'm sorry, the board is writing like a spooky, so 0.05 instead of 5%. All right, but it's 0.05, and this time it's going to be quarterly, so we're going to divide this by 4, and we're going to raise this for 1 year would be 4 times 1, which would be 5.09%. Monthly would be 1 plus 0.05 divided by 12. The whole thing raised to the 12 times 1 for 1 year would be 5.12%. And then we have daily, which almost never happens, which means we would have 1 plus 0.05 divided by 365 days, assuming we're not on a leap year, times 365 times 1, which is 5.13. Okay? I'm going to remind you, every time I did this, I'm sorry I kind of skipped this step. Like I skipped the step here because this is equal to 1.05116, and then I minus the 1, I got 0.05116, and then I moved it over 2 places. I'm sorry, I skipped that step, and maybe I shouldn't have. All right, just to go back quickly to this one. When I found this one, this would have been 1.05094. Remember, we always subtract out our 1, which is 0.05094. And then I moved it over 2 more places to find my percentage, and this becomes 5.09%. I did the same thing on the daily one on the right-hand side. So if you're doing the math at home and you're not wondering where the 5.09 is coming from and the 5.12 is coming from, now you know. Okay? So if you were going to do this last one, once you do the math here, this one comes out to be 1.05126. Subtract out the 1, you get 0.05126. Multiply by 100, or move the decimal point 2 places, you get 5.126. And then we just round it to the nearest hundredth, and that's where the 5.13 comes from. Okay, my apologies. Sometimes I skip steps without taking into consideration you not understanding where they come from. All right, so if you need to back that up and look at it one more time, feel free to. Pause the video, write down what you need to, and I'll meet you at exercise 5. We could compound at smaller and smaller frequency intervals, eventually compounding all moments of time. In our formula from exercise number 3, we would be letting n approach infinity. Interestingly enough, this gives rise to continuous compounding and the use of the natural base e in the famous continuous compound interest formula. So, for an initial principal p, compounding continuously at a nominal yearly rate, the investment would be worth an amount A given by A of t is equal to P being your principal or your initial amount times the number E raised to the RT, R being the rate, T being the time. All right, so let's take a look at how to apply that in exercise 5. A person invests $350 in a bank account that promises a nominal rate of 2% continuously compounded, and that is what you're looking for. The nominal rate and then continuously compounded. As soon as you hear that, you know this is the formula we're going to be using. So it says write the equation for the amount this investment would be worth after t years. We'll use your formula, very simple. So a sub t is equal to 350 is my initial amount times, oh, you know what, you really don't need the parenthesis. 350 times e raised to the 0.02, there's my rate, 2%, 0.02, times my time, which in this case I don't know. All right, and then B says how much would the investment be worth after 20 years? So this means we're just going to put this into our calculator now, is equal to 350 times e to the 0.02 times 20. And once you put that whole thing into your calculator, you get 522, 13864, and of course we're talking money here, so it's going to be $522.14. I think that was straightforward enough. So let's slide down to C now. Algebraically determine the time it would take for an investment to reach $400. All right, so in this case now, we are going to take our 350 times e to the 0.02t and set it equal to 400. Now you could have put the 400 in the front, but like I always tell you, I do not like that t on the right-hand side, so I'm going to rewrite it this way. We need to isolate our base, which is e, so we're going to divide both sides by 350, and e to the 0.02t is equal to 400 divided by 350. Again, you could reduce it, but really there's no reason to. So now we're going to log both sides. What the heck is wrong with this board? We're going to log both sides, but because we're working in a base e, we're going to natural log both sides. So we're going to do the natural log, okay, of e to the 0.02t is equal to the natural log of 400 divided by 350. And this is going to work out beautifully because now when we pull this out front, remember, same laws as we did before. So 0.02t times ln of e is equal to the ln of 400 over 350. And the ln of e we learned from our last lesson is equal to 1. So you have 0.02t is equal to ln of 400 divided by 350. And simply now divide both sides by 0.02. You put this whole thing into your calculator, and t turns out to be 6.676, and we are told to round it to the nearest tenth of a year, so t is equal to 6.7 years. Okay. I'm sorry, I did things out of order there. I'm just realizing that I missed. Oh no, I didn't. There we go. D is next. I thought I missed B, but I did B. So what is the effective annual rate for this investment? Round to the nearest hundredth of a percent. So that nearest effective annual rate is going to be e to the 0.02 times 1 per year is equal to 1.0202. Let's not skip steps this time. Minus 1, I get 0.0202. Now it wants the nearest percent annual rate, so we're going to do it in a percent, the nearest percent. We're going to multiply by 100, or move your decimal point 2 places to the right, and you get 2.02%. All right, so as you can see, it's higher than your nominal rate. Your nominal rate is 2%. You're making more than that. You're making 2.02%, which is always a good thing. Whoop, there's the bell, so that means I must be done. So I'll see you tomorrow in class, and until then, make good choices. Okay, bye now.